What if I told you that time isn't constant, that it can stretch and warp like taffy, depending on where you are in the universe, or that black holes, those cosmic vacuum cleaners, don't just swallow light, they slow time itself to a crawl. These aren't just wild ideas from a sci-fi movie, they're real, mind-bending truths about the fabric of reality. Space and time aren't just the backdrop of our lives. They're dynamic, mysterious forces that shape everything from the tiniest atom to the vastest galaxy. And today, we're diving deep into 25 astonishing facts that will twist your understanding of the cosmos in ways you never saw coming. Think about this. Right now, as you watch this video, time is passing slightly faster for your head than it is for your feet. It's true, thanks to gravity's grip on reality. Time ticks slower the closer you are to Earth's surface. That's just one of the bizarre, beautiful quirks of Einstein's theory of relativity, a theory that upended everything we thought we knew about space and time. But that's barely scratching the surface. Did you know there are places in the universe where a single hour could equal 7 years on Earth? Or that the vacuum of space isn't really empty, it's boiling with particles popping in and out of existence. The more we learn, the clearer it becomes. The universe is far stranger, far more wondrous than we ever dared to imagine. So buckle up. Over the next few minutes, we'll unravel cosmic mysteries that defy common sense, from the mind-blowing speed of light, which isn't as constant as you might think, to the chilling possibility of parallel universes lurking just beyond our perception. This isn't just a list of facts, it's a journey to the edge of human understanding, where the laws of physics bend and the very nature of reality gets turned inside out. Whether you're a space enthusiast or just someone who loves a good cosmic head-scratcher, what you're about to discover will leave you seeing the universe and your place in it in a whole new light. Ready? Let's jump in. Let's start with something that sounds like pure science fiction, but it's absolutely real. Picture a black hole, one of the most extreme objects in the universe, where gravity is so intense that not even light can escape. But here's the wild part. If you could hover near the edge of a black hole, just close enough not to get sucked in, time itself would slow down for you compared to someone far away in space. This isn't just a theory, it's one of the most mind-bending predictions of Einstein's general relativity. Gravity doesn't just pull on objects, it warps the very fabric of time. Think of it like this. Imagine two identical clocks, one placed on Earth and the other near a black hole's edge. The clock near the black hole would tick much slower than the one on Earth. If you could watch from a safe distance, you'd see someone near the black hole moving in slow motion, aging at a fraction of the normal rate. For them, minutes might pass while decades fly by elsewhere in the universe. This isn't some illusion. Time itself is stretching, bending under the black hole's immense gravitational pull. Einstein showed us that space and time are woven together into a single fabric called spacetime, and gravity is what happens when massive objects like black holes dent that fabric. The stronger the gravity, the deeper the dent, and the slower time flows. Astronomers have even observed this effect in real life. Near supermassive black holes at the centers of galaxies, light from stars gets stretched into longer, redder wavelengths, a phenomenon called gravitational redshift, proving that time itself is being warped. Now here's where it gets even stranger. If you could somehow survive a trip close to a black hole and then return to Earth, you'd find that everyone you knew had aged far more than you. It's like stepping into a cosmic time machine, except instead of moving through time, you're changing how fast time moves for you. This isn't just a curious quirk of physics, it has real implications for how we understand the universe. Black holes aren't just cosmic vacuum cleaners, they're time-bending laboratories, showing us that reality is far more flexible than our everyday experience suggests. And if that doesn't make you question everything you thought you knew about time, just wait, we're only getting started. Here's something that might seem impossible at first glance. The universe is expanding faster than the speed of light. Wait, doesn't Einstein's relativity say nothing can go faster than light? Well, yes, but there's a cosmic loophole. The speed limit applies to objects moving through space, not to space itself stretching. Picture a loaf of raisin bread baking in the oven. As it rises, the raisins move apart not because they're traveling through the dough, but because the dough itself is expanding. That's exactly what's happening to our universe. Galaxies aren't speeding away from us, the space between us and them is growing. And over vast distances, that expansion adds up to speeds that leave light in the dust. This mind-blowing discovery traces back to astronomer Edwin Hubble in the 1920s. By observing distant galaxies, he noticed something peculiar. The farther away a galaxy was, the faster it appeared to be moving away from us. At first, scientists assumed gravity would eventually slow this expansion down. But in the late 1990s, two teams of researchers made an even more startling find. The universe's expansion isn't slowing at all. It's accelerating. Something invisible, dubbed dark energy, is pushing galaxies apart faster and faster. Today, we think dark energy makes up about 68% of the universe, acting like an anti-gravity force that's stretching space-time itself. Here's where it gets truly wild. Because this expansion is happening to space itself, it doesn't violate relativity's cosmic speed limit. Imagine standing on a moving walkway holding a flashlight. The light beams out at light speed, but if the walkway accelerates beneath you, the total speed of the light relative to the ground could exceed light speed without the photons themselves breaking any rules. That's the universe in a nutshell. Distant galaxies aren't moving through space faster than light. The space between us is swelling, carrying them away like driftwood on a rising tide. The implications are staggering. Over billions of years, galaxies beyond our local group will vanish over the cosmic horizon, their light stretched too thin for us to ever detect. The universe will become a far lonelier place, and we're watching it happen in real time. What's driving this runaway expansion? Dark energy remains one of physics' greatest mysteries. Some theories suggest it's the energy of empty space itself, while others propose entirely new laws of physics. One thing's certain: the universe isn't just expanding. It's racing into the unknown, and we're just beginning to unravel why. Out in the cosmic expanse, hidden among the sea of galaxies, lies one of the universe's most baffling mysteries. A yawning chasm of nothingness so vast it defies explanation. Known as the Boötes Void, this eerie region stretches an astonishing 330 million light-years across, a staggering emptiness where galaxies should be clumped together by the thousands. Instead, astronomers have found only a scant few dozen, scattered like lonely islands in an ocean of darkness. If you were to place the Milky Way at the center of this void, we wouldn't have even detected another galaxy until the 1960s. That's how empty it is. How does something like this even form? The leading theory suggests it might be the ghostly imprint of an ancient collision between bubble universes, a cosmic crash so colossal it left behind a scar in the fabric of our own universe. Imagine two soap bubbles brushing against each other. Where they meet, matter gets pushed aside, creating a hollow space. Some physicists speculate that the Boötes Void could be the aftermath of such an encounter, a place where our universe bumped against another, leaving behind this incomprehensible blank spot. But there's another, even more radical idea. What if this void isn't natural at all? Some have theorized, half seriously, that an ultra-advanced civilization could have harnessed the energy of entire galaxies, leaving behind a vast engineered emptiness. While there's zero evidence for this, it's a chilling thought. Could the Boötes Void be the universe's ultimate construction site, a place where something unimaginable was built or dismantled? What makes this void even stranger is that it shouldn't exist under our current understanding of the cosmos. The universe, according to the Big Bang theory, should be roughly uniform, with matter distributed fairly evenly. Yet here we have a region so empty it's like a hole punched through reality itself. When astronomers first mapped it in the 1980s, they were stunned. It was like finding a desert the size of a continent in the middle of a dense forest. And the Boötes Void isn't alone. Other enormous voids have been discovered since, though none quite as extreme. These cosmic deserts challenge our models of galaxy formation and the large-scale structure of the universe. If voids this big can exist, what does that say about the forces shaping the cosmos? Are they evidence of exotic physics we haven't yet uncovered, or just the natural result of gravity's uneven tug over billions of years? One thing certain, the Boötes Void is a humbling reminder of how much we still don't understand. It's a cosmic anomaly that refuses to fit neatly into our theories, a silent enigma lurking in the darkness. And as we peer deeper into the universe, who knows what other unimaginable structures we might find waiting to shatter our assumptions once again. Now let's talk about one of the most extreme objects in the universe, neutron stars. These cosmic oddities are so dense, a single teaspoon of their material would weigh an unimaginable billion tons. To put that in perspective, imagine taking Mount Everest, every rock, every crevice, all 290,000 million tons of it, and crushing it down into something the size of a sugar cube. That's the kind of insane density we're dealing with here. So how does something like this even form? It all starts with a massive star, at least 8 times heavier than our Sun. When such a star runs out of fuel, it doesn't go quietly. It explodes in a supernova, one of the most violent events in the cosmos. The outer layers blast away into space while the core collapses under its own gravity. And when gravity wins, it doesn't mess around. The collapse is so intense that electrons and protons are squeezed together, merging into neutrons. What's left is a city-sized ball of nearly pure neutron matter, packing more mass than our Sun into a sphere just 12 miles across. But here's the wild part: neutron stars don't just sit there. Many spin at dizzying speeds, rotating hundreds of times per second. Some even whip beams of radiation across space like interstellar lighthouses, earning the name pulsars. And if you thought their density was extreme, their surfaces are no less mind-bending. The gravity on a neutron star is so strong that if you dropped a marshmallow from just a meter above its surface, it would hit with the energy of a nuclear bomb. That's not an exaggeration. Their gravitational pull warps space-time so severely that even light struggles to escape. What makes these objects truly fascinating is how they push the limits of physics. The matter inside a neutron star is so compressed that it enters states we can't replicate on Earth. Some theories suggest their cores might contain exotic particles or even free-floating quarks, stuff that exists nowhere else in the universe. Others speculate that if a neutron star gets just a little too heavy, it'll collapse further, turning into a black hole. And here's a chilling thought: if 2 neutron stars collide, the resulting explosion creates ripples in space-time itself, sending gravitational waves across the cosmos. These collisions forge heavy elements like gold and platinum, meaning the ring on your finger might have come from one of the universe's most violent reunions. Neutron stars are more than just cosmic curiosities, they're extreme laboratories, showing us just how strange and wondrous the universe can get when the rules of physics are pushed to the breaking point. Hidden behind the thick dust and stars of our own Milky Way lies one of the most puzzling gravitational mysteries in the cosmos, a force so powerful it's dragging entire galaxies, including ours, toward it at over 14 million miles per hour. Astronomers call it the Great Attractor, and despite decades of study, we still don't fully understand what it is. Picture a cosmic game of tug-of-war, where every galaxy in our corner of the universe is being pulled toward something we can't even see clearly. The story begins in the 1970s when scientists noticed something strange. All the galaxies in our local supercluster, including the Milky Way, were moving in the same direction, as if drawn by an invisible hand. At first, they assumed it was the pull of known galaxy clusters like Virgo, but when they crunched the numbers, the math didn't add up. There had to be something bigger, something unseen, exerting an even stronger gravitational pull. That's when they realized we're being lured towards something colossal lurking behind the dense plane of our own galaxy, where dust and stars block our view. What could this mysterious attractor be? The leading theory suggests it's a massive concentration of galaxies, a supercluster so dense its gravity dominates everything around it. Observations hint at a structure called the Norma cluster at its heart, packing thousands of galaxies into a relatively small space. But here's the twist, even that might not fully explain the staggering pull we're experiencing. Some researchers speculate there's something even larger at play, like a confluence of multiple superclusters forming a great wall of galaxies, with gravity weaving them into a single, irresistible force. And then there's the more radical possibility: what if the Great Attractor isn't the end of the story? In recent years, astronomers have detected an even bigger, more distant structure called the Shapley supercluster, which might be pulling the Great Attractor itself. It's like peeling back layers of a cosmic onion, each one revealing a larger, more influential gravitational player. The real challenge in solving this mystery comes down to our limited viewpoint. From Earth, we're stuck peering through the zone of avoidance, a region of the sky obscured by our galaxy's dust and gas. It's like trying to spot a distant city through a dense fog. Only with advanced infrared and radio telescopes have we begun to glimpse the shadowy outlines of what's pulling us. One thing's certain: the Great Attractor forces us to confront how little we truly know about the large-scale structure of the universe. It's a humbling reminder that even as we map the cosmos, there are still invisible hands shaping our galactic neighborhood, their secrets waiting just out of sight. And as our telescopes grow more powerful, who knows what other gravitational giants we might find silently steering the motion of galaxies across the universe. What if everything you think you know about time is just an illusion, that the past, present, and future aren't slipping away but exist simultaneously, frozen in place like frames in a film? This isn't some psychedelic thought experiment. It's a serious theory in physics called the block universe. Imagine the entire cosmos as a vast, unchanging four-dimensional block where every moment from the Big Bang to the heat death of the universe already exists, stacked together like pages in a book. Your birth, your first steps, even the moment you're watching this video right now, they're all equally real, just occupying different coordinates in space-time. Think of it like a DVD. When you pop in a movie, all the scenes are already there on the disc, complete and unchanging. You might watch them in sequence, but that doesn't mean the earlier scenes cease to exist when you reach the end. The block universe suggests reality works the same way. The now you're experiencing is just the point where your consciousness happens to be scanning across this frozen timeline. It's a radical departure from how we intuitively experience time, where the past feels gone and the future feels unwritten. Einstein's relativity hints at this idea. In his equations, time isn't some universal metronome ticking at the same rate for everyone. It's fluid, bending around gravity and motion. If you could peer at Earth from near a black hole, you'd see our planet's history unfold in fast forward, like hitting fast forward on a cosmic remote. But here's the kicker: from Earth's perspective, time near the black hole would appear to crawl. There's no single now that applies everywhere. This relativity of simultaneity fractures our everyday notion of time, making the block universe a compelling framework for physicists. So why does time feel like it's flowing? That's the million-dollar question. Some theories suggest our conscious experience creates the illusion of movement, like a spotlight sweeping across the frozen landscape of spacetime. Others propose that entropy, the universe's tendency toward disorder, creates an arrow of time, giving us the sense of past versus future. But in the block universe, even that arrow is just part of the larger, unchanging structure. Here's where it gets even weirder. If the future already exists, does that mean free will is an illusion? Not necessarily. the block universe could simply be the map of every choice you'll ever make, with your decisions still shaping the path. It's like reading a novel. The ending is already written, but the characters don't know it yet. This theory isn't just philosophical musing. It helps resolve paradoxes in physics, like how particles in quantum entanglement seem to communicate instantly across distances, defying the speed of light. In the block universe, their connection isn't breaking the rules. It's woven into the fabric of space-time itself. Whether this is the true nature of reality or just a useful model, one thing's certain: time is far stranger than our brains are wired to perceive. The next time you glance at a clock, remember, you're not just watching time pass. You're stepping through an eternal mosaic where every moment, from the dawn of the cosmos to its final whisper, is already set in stone. Somewhere in the constellation Cancer, 40 light-years from Earth, orbits a world that would make even the most extravagant jeweler gasp, a planet literally made of diamond. Known as 55 Cancri E, this scorching super-Earth is so carbon-rich that under its extreme pressure and heat, scientists believe much of its interior has crystallized into one massive diamond. Picture a world twice the size of ours, where mountains might not be made of rock, but of glittering gemstone, and rivers of molten diamond could flow across its surface. How does such a dazzling nightmare come to exist? It starts with the planet's composition. Carbon makes up nearly a third of its mass, compared to Earth's measly 0.005%. Formed in a carbon-heavy star system, 55 Cancri E essentially hit the cosmic lottery, drowning in the raw ingredients for diamond creation. Add to this a surface temperature hot enough to melt steel, around 4,200 degrees Fahrenheit, and pressures millions of times greater than Earth's, and you've got the perfect forge for turning carbon into something far more exotic. But here's the burning question: would this planet actually sparkle like a cosmic gemstone? The answer is far stranger. While parts of its interior are likely solid diamond, the surface is probably a hellish wasteland of graphite, the same stuff in your pencil, with seas of molten carbon. At those temperatures, exposed diamond would vaporize or dissolve, meaning the real treasure might lie buried beneath layers of scorching sludge. Imagine digging through miles of boiling tar only to strike a diamond core the size of a continent, a jewel so vast it would dwarf every diamond ever mined on Earth combined. Yet, even if we could never mine it, 55 Cancri E offers something priceless: proof that the universe cooks up wonders beyond our wildest fantasies. It challenges our assumptions about what planets can be, showing us worlds forged not just from rock and gas, but from the very elements we treasure here on Earth. And it raises a tantalizing thought: if diamond planets exist, what other impossible worlds might be hiding in the dark, ruby-crusted giants, sapphire oceans? The cosmos, it seems, has a flair for the extravagant, but don't pack your space bags just yet. With a year lasting just 18 hours and gravity twice as strong as Earth's, standing on this jewel world would crush you while its lead-melting heat vaporized your remains. Perhaps it's better admired from afar, a glittering reminder that the universe is richer, stranger, and more imaginative than anything we could invent. Look up at the moon tonight, and you're seeing a cosmic relationship in slow motion, because right now, our lunar companion is creeping away from Earth at about the same speed your fingernails grow. Every year, the moon drifts 3.8 centimeters farther into space, carried by the invisible tug of war between Earth's rotation and the moon's gravity. This gentle but relentless movement might seem insignificant, but over cosmic timescales, it's rewriting the very rhythm of our planet. Here's how it works. The moon's gravity creates tides not just in Earth's oceans, but in the solid rock beneath us too. As Earth spins, these tidal bulges lag slightly behind, pulled by the moon's gravity. This creates a drag on our planet's rotation, slowing it down by about 2 milliseconds per century. But there's a twist: just as Earth loses energy, the moon gains it, flinging itself into a higher orbit. It's a celestial dance where momentum gets traded like currency, with Earth gradually handing over its spin to the Moon's orbit. Now fast forward 1 billion years. With the Moon farther away, tides would weaken to a fraction of their current strength, turning coastal ecosystems upside down. Coral reefs that rely on tidal currents could suffocate in stagnant water, while species that evolved to sync with lunar cycles like horseshoe crabs spawning at high tide might face extinction. But the changes wouldn't stop there. Earth's days, which have already grown from just 6 hours in the planet's infancy to our current 24, would stretch even longer. By the time the Moon reaches its maximum distance, about 1.5 times its current orbit, a day on Earth could last 47 of our present hours. The most startling part, this drifting isn't forever. Eventually, the Sun's death throes will disrupt this delicate balance. In about 5 billion years, as our star swells into a red giant, solar tides will overpower the Moon's influence, dragging it back toward Earth. But long before that fiery finale, the Moon's retreat will have reshaped our world beyond recognition. This slow-motion escape reveals a profound truth: even the most familiar cosmic relationships are temporary. The Moon we take for granted, the tides that shape our shores, the length of our days, they're all part of an ever-changing cosmic clock, ticking toward a future where Earth and Moon will gaze at each other across a much wider abyss. Deep in the constellation Libra, a faint yellow star flickers with an impossible secret. It appears to be older than the universe itself. Known as HD 140283, or the Methuselah star, this ancient stellar relic has astronomers scratching their heads. When researchers first calculated its age using well-established stellar evolution models, they arrived at a jaw-dropping figure around 14.5 billion years old. There's just one problem. The universe, according to our best measurements, is only 13.8 billion years old. That's like finding a birth certificate claiming someone is older than their hometown's founding date. So how could a star exist before the cosmos itself? The answer lies in the tricky business of cosmic timekeeping. Determining a star's age isn't as simple as counting rings on a tree. It involves analyzing its chemical composition, brightness, and motion through space. The Methuselah star is especially puzzling because it contains almost no iron, suggesting it formed before this element became common in the universe. Early stars were made almost entirely of hydrogen and helium, forged in the aftermath of the Big Bang. The lack of heavier elements in HD 140283 points to an extraordinarily ancient origin. But this creates a glaring contradiction with our current understanding of cosmic history. If the star really predates the universe, that would upend everything we know about physics. To resolve the paradox, scientists have proposed several intriguing solutions. One possibility is that the Hubble constant, the rate at which the universe is expanding, might need slight revision. A faster expansion rate would mean the universe is slightly older than we thought, potentially closing the gap. Another explanation involves tweaking our models of stellar evolution, accounting for factors like unusual mixing processes inside the star that could make it appear older than it is. Recent studies using updated data from the Hubble Space Telescope have narrowed the Methuselah star's age to roughly 14.27 billion years, with a margin of error that just barely overlaps with the universe's age. While this eases the tension, the mystery isn't completely solved. If our cosmic timeline holds firm, this star must have formed impossibly early within the universe's first few 100 million years, when galaxies were still taking shape. That alone would rewrite our understanding of how quickly the first stars ignited after the Big Bang. What makes this star so fascinating isn't just the numbers, it's what it represents. The Methuselah star is a cosmic detective story, forcing us to question whether our measurements are flawed, our models incomplete, or our grasp of cosmic history fundamentally mistaken. Like finding a 500-year-old tortoise, it hints at processes and timelines we might not yet comprehend. Whether the final answer lies in recalculating the universe's expansion or reimagining stellar formation, one thing is clear: this ancient beacon is teaching us that the universe might have more wrinkles in its timeline than we ever imagined. Imagine two coins flipped on opposite sides of the universe. No matter how far apart they are, they always land showing the same face. Now replace those coins with subatomic particles, and you've got one of the most baffling phenomena in physics: quantum entanglement. Einstein famously called it spooky action at a distance, a phrase that captures just how unsettling this idea was even for the genius who reshaped our understanding of space and time. Here's how it works. When two particles become entangled, they share a quantum connection so profound that measuring one instantly determines the state of the other, no matter if they're a millimeter or a galaxy apart. This isn't just fast communication, it's instantaneous, defying the cosmic speed limit set by light. And that's exactly what troubled Einstein. In his view, nothing could influence anything else faster than light could travel between them. He argued that if entanglement appeared to break this rule, it must mean our understanding of quantum mechanics was incomplete, that some hidden variables were at play, secretly coordinating the particles' behavior behind the scenes. But decades of experiments have proven Einstein wrong in the most dramatic way possible. In the 1980s, physicist Elaine Aspect conducted groundbreaking tests that showed entangled particles really do influence each other faster than light could cross the distance between them. And it's not just a fluke. Repeat studies using everything from photons to diamonds have confirmed it. The universe, at its most fundamental level, operates in ways that defy our everyday intuition about how reality should work. What makes entanglement even stranger is that it doesn't involve any detectable signal or energy transfer. It's as if the particles aren't communicating at all but exist in a shared state that transcends space. Picture two dice in separate boxes. Opening one to reveal a 6 doesn't send a message to the other die. It simply means both were always 6s even before you looked. In the quantum world, particles don't have definite properties until measured, and entanglement forces them to choose matching states instantly, no matter the distance. This raises mind-bending questions. Could entanglement hint at a deeper layer of reality where space isn't what we think? Some theories propose that space-time emerges from a more fundamental quantum fabric, with entanglement acting as the stitching that holds it together. Others suggest that entangled particles aren't truly separate at all, that their connection reveals a universe far more interconnected than we ever imagined. Yet for all its mystery, entanglement isn't just theoretical. It's the backbone of emerging technologies like quantum computing and ultra-secure communication. By harnessing these spooky links, we're building machines that could solve problems in seconds which would take conventional computers millennia. The same phenomenon that baffled Einstein might one day revolutionize our world. So the next time you feel alone in the universe, remember, at the quantum level, particles separated by light years can still dance in perfect, inexplicable synchrony. The cosmos, it seems, has a way of keeping things connected that we're only beginning to understand. If you could take a deep breath in deep space, which, let's be clear, you absolutely shouldn't, you might catch a whiff of something unexpectedly familiar. The vast molecular clouds drifting through our Milky Way are packed with complex organic compounds, and one in particular, ethyl formate, happens to smell strikingly like rum mixed with raspberries. That's right, our galaxy has the aromatic signature of an interstellar cocktail bar, where cosmic mixologists have been brewing fragrant molecules for billions of years. This bizarre discovery came from the heart of Sagittarius B2, a gargantuan dust cloud near the center of the Milky Way. Using powerful radio telescopes, astronomers detected the chemical fingerprints of ethyl formate floating in space, the same compound that gives raspberries their fruity sweetness and rum its distinctive edge. But it's not alone. This cosmic pantry also contains ethyl alcohol, yes, the drinkable kind, along with vinegar like acetic acid, and even the buttery scented molecule responsible for popcorn's mouth-watering aroma. Taken together, the center of our galaxy might smell like a bizarre fusion of a bakery, a distillery, and a candy shop. Now, before you picture floating through space with a cocktail glass, here's the catch. These molecules are spread impossibly thin, with concentrations so low you'd never actually detect their scent. A single whiff of a real interstellar cloud would likely just freeze or suffocate you long before your nose picked up any fruity notes. But the fact these compounds exist at all is mind-blowing. They're proof that the same basic building blocks of flavor, and even life, are being manufactured in the cold void between stars, forged by the subtle chemistry of radiation and dust. What's even wilder, these molecules might hold clues to how life began. Ethyl formate and its cocktail companions belong to a class of compounds called esters, which are key players in organic chemistry. Some scientists speculate that these fragrant molecules could have hitched rides on comets or asteroids, seeding young planets like Earth with probiotic ingredients. The same processes that make space smell like a tiki bar might have set the stage for DNA, proteins, and eventually, us. So the next time you sip a rum cocktail or bite into a raspberry, remember, you're tasting a flavor that perfumes the cosmos. The universe isn't just a silent vacuum. It's a vast, invisible kitchen where the recipes for life, and maybe even a good drink, are written in the language of chemistry. Cheers to that. There's something lurking in the icy darkness beyond Neptune, something massive enough to tug on the orbits of distant worlds, yet invisible to our telescopes. Scientists call it Planet 9, a hypothetical giant that could rewrite our solar system's map. The clues started piling up in 2014 when astronomers noticed something odd. A cluster of small icy objects in the Kuiper belt, all swinging around the sun on strangely tilted orbits, as if an unseen hand were herding them. These frozen worlds shouldn't align like this by chance. Their paths suggest the gravitational fingerprint of something big, perhaps 5 to 10 times heavier than Earth. The hunt for Planet 9 reads like a cosmic detective story. Researchers have run countless simulations, and the math keeps pointing to the same conclusion. Only a distant, super-Earth-sized planet could explain these orbital anomalies. If it exists, it's likely an ice giant with a colossal, looping orbit, taking between 10,000 and 20,000 years to circle the Sun. Picture this, a frozen world so far out that the Sun would appear as little more than a bright star in its pitch-black sky. At that distance, sunlight would take weeks to reach it, and our strongest telescopes might miss it entirely against the in-sky backdrop of space. So why haven't we found it yet? Part of the challenge is the sheer scale of the search. Planet 9 could be anywhere along its enormous orbit, and spotting a cold, dark object in that vastness is like searching for a single dimmed headlight in a foggy desert. But astronomers aren't giving up. Teams are scouring the sky with tools like the Subaru telescope in Hawaii, methodically stitching together years of images to catch any faint movement against the stars. The Vera C. Rubin Observatory, set to come online in 2025, might finally settle the debate with its unprecedented wide-field view of the cosmos. What's at stake isn't just another planetary addition to our solar system's lineup. If Planet 9 is real, it could explain mysteries that have puzzled scientists for decades, like why the solar system's plane is slightly tilted, or how some distant objects ended up on such eccentric paths. Some theories even suggest it might be a rogue planet captured by the Sun's gravity long after the solar system formed, a cosmic immigrant hiding in plain sight. The wait for answers is agonizing. Every new discovery in the Kuiper belt either strengthens the case or adds fresh wrinkles to the mystery. One thing's certain: whether Planet 9 turns out to be a real world or a celestial ghost story, its legend has already reshaped how we see our cosmic neighborhood. The outer solar system might be far from empty. It could be hiding one of the biggest discoveries of our time, quietly waiting for its moment in the spotlight. Light zipping through space at 670 million miles per hour still takes an astonishing 100,000 years to travel from one end of our Milky Way to the other. Wrap your head around that: a single photon, the fastest thing in the universe, spends longer crossing our home galaxy than modern humans have existed as a species. To put it another way, if that photon set out on its journey when early humans first began migrating out of Africa, it would only now be reaching the Milky Way's far side. Picture the Milky Way as a colossal disk of stars, gas, and dust stretching 100,000 light-years across. That's 587,850 trillion miles, a number so vast it loses all meaning. Here's a better way to visualize it. Imagine shrinking our galaxy down to the size of North America. At that scale, light would take roughly 2.5 hours to cross from Los Angeles to New York. But here's the catch: in reality, light makes that same trip in a fraction of a second on Earth. The Milky Way's true scale is so enormous that even light, which could circle our planet 7.5 times in a single second, crawls across it at a glacial pace. Now consider what that photon would witness on its epic journey. Near the galaxy's edge, it might dart past solitary red dwarfs and drifting nebulae. As it nears the crowded core, it would weave through a maze of stars packed thousands of times tighter than in our solar neighborhood, dodging black holes and neutron stars along the way. And here's the cruel irony: by the time that photon finally reaches its destination, the stars it passed at the beginning of its trip may have long since died, their light already faded into cosmic history. This mind-bending timescale reveals just how small we really are. Our entire written history, every war, invention, and civilization, fits into a sliver of time shorter than a single galactic breath. The Milky Way doesn't just dwarf us in size, it operates on a clock that makes human lifetimes vanish into statistical noise. Yet somehow we've mapped its shape, measured its motions, and even sent probes beyond our solar system. That's the paradox of cosmic perspective. We're insignificant in time and space, but our curiosity reaches further than light itself. The world around you, the screen you're staring at, the chair you're sitting on, even the stars in the night sky might not be what it seems. What if I told you our entire three-dimensional universe could be a cosmic illusion, a holographic projection encoded on a distant two-dimensional surface? This isn't science fiction, it's a serious theory called the holographic principle, and it emerges from one of physics' most perplexing puzzles: what happens to information that falls into a black hole? Black holes, those ultimate cosmic traps, don't just swallow matter, they devour information. Every particle that crosses their event horizon carries data about its properties, from position to spin. According to quantum mechanics, information can never truly be destroyed. But if nothing escapes a black hole, where does all that information go? In the 1970s, physicist Stephen Hawking discovered that black holes slowly evaporate, leaking radiation over eons until they vanish entirely. This raised a terrifying possibility: if the black hole disappears, does the information it consumed vanish too, violating quantum law? Enter the holographic principle. Theorists like Gerard T. Hooft and Leonard Susskind proposed a radical solution. The information isn't lost, it's smeared across the black hole's event horizon like data etched onto a celestial hard drive. Imagine a bubble with a soap film. Everything inside the bubble, the air, the swirling patterns, could theoretically be described by vibrations on the film's surface. Similarly, the holographic principle suggests our three-dimensional reality might be encoded on a two-dimensional boundary at the edge of the universe, with every event inside, from supernovas to your morning coffee, being a projection of that data. Here's where it gets even stranger. In the late 1990s, physicist Juan Maldacena mathematically proved a version of this idea using string theory. His work showed that a hypothetical universe with certain properties could be perfectly described by physics operating on its lower dimensional boundary, like a cosmic DVD where the three-dimensional movie is encoded on a two-dimensional disc. While our universe isn't identical to Maldacner's model, the implications are staggering. Space itself, with all its depth and volume, might be emergent, a secondary effect of information processing happening somewhere else entirely. What does this mean for us? If the holographic principle holds, reality as we experience it could be akin to a video game rendered in real time, where the true code exists on a hidden surface we'll never see. It challenges our most basic assumptions about existence, suggesting that space, time, and even gravity might not be fundamental, just convenient illusions born from a deeper, more abstract layer of reality. So next time you reach out to touch something solid, remember, there's a chance you're interacting with the universe's most convincing mirage, a shadow play cast from the edges of existence itself. Venus is the solar system's ultimate cosmic paradox, a world where a single day drags on longer than an entire trip around the sun. While Earth pirouettes once every 24 hours, Venus takes a sluggish 243 Earth days to complete just one rotation. But here's the real kicker, it only needs 225 days to circle the sun. That's right, on Venus, your birthday would come before your next sunrise. So how did this upside-down rhythm come to be? The leading theory points to gravitational tides playing the ultimate cosmic break. Picture Venus as a spinning top immersed in the sun's gravitational field. Over billions of years, the sun's relentless pull may have slowed Venus's rotation, like an invisible hand gently pressing against its motion. But there's a twist: Venus didn't just slow down, it likely flipped entirely. Some models suggest the planet started with a typical prograde rotation, spinning counter-clockwise like Earth before gravitational interactions with its thick, soupy atmosphere and the sun's tidal forces literally turned it backward. Today, Venus rotates clockwise, the only planet in our solar system to do so. This sluggish spin creates surreal conditions. The Venusian surface is stuck in perpetual twilight, with the sun creeping across the sky at a pace slower than a melting glacier. If you stood on its scorching surface, you'd witness a sunrise every 117 Earth days, but don't expect a refreshing dawn. With surface temperatures hot enough to melt lead and an atmosphere 92 times thicker than Earth's, daylight on Venus feels less like a new beginning and more like a slow bake in a pressure cooker. What's even stranger is how this extreme rotation affects timekeeping. A Venusian year, one full orbit around the sun, is over 18 Earth days shorter than its day. That means if Venus had calendars, they'd reset annually before the date even needed changing. But the real mystery isn't just its bizarre clock. It's why Venus ended up this way while Earth, its so-called twin, spins so differently. Some scientists speculate that a colossal collision, similar to the impact that birthed Earth's moon, might have sent Venus into its backward spiral. Others point to its dense, hurricane-force atmosphere. Tides from its own atmospheric drag could have sapped its rotation speed like a planetary parachute. Every new mission to Venus, from NASA upcoming Veritas to ESA's Envision, brings us closer to solving these riddles. As we peel back the layers of its toxic clouds, we're not just studying another world, we're unraveling a cautionary tale about how delicate the balance of planetary motion can be. Venus is a reminder that even in the predictable clockwork of the solar system, time can twist in ways that defy all expectations. Take a handful of sand from any beach, and you're holding more grains than you could possibly count in a lifetime. Now multiply that by every beach, every desert, every speck of sand on Earth, every grain that's ever existed. The total comes to around 10 quintillion, or 10 raised to the power of 18. A number so vast it defies comprehension. Yet, unbelievably, the cosmos holds 10,000 times more stars than all those grains combined. That's right, scientists estimate there are roughly 100 billion galaxies in the observable universe, each brimming with hundreds of billions of stars. Multiply those numbers and you get a staggering 10 raised to the power of 22 stars, a 1 followed by 22 zeros. To put that into perspective, if every grain of sand on Earth magically transformed into another Earth, and each of those Earths had its own entire supply of sand, that would still only get you halfway to the number of stars in the universe. The scale is so immense, our brains simply aren't wired to grasp it. The Hubble Space Telescope gave us a glimpse of this cosmic abundance with its famous ultra-deep field image. For over 11 days in 2003 and 2004, Hubble stared at what appeared to be an empty patch of sky, a slice no bigger than a grain of sand held at arm's length. The result, a mind-blowing tapestry of 10,000 galaxies, each a sprawling metropolis of stars, planets, and possibilities. And here's the kicker, that tiny sliver of space represents just 1/12 millionth of the entire sky. Now imagine this, if Hubble could capture 10,000 galaxies in a pinprick of darkness, then across the full celestial sphere, there could be hundreds of billions more waiting to be seen. Every point of light in that image isn't just a single star, it's an entire galaxy with its own swirling arms, glowing nebulae, and potentially habitable worlds. And that's just the observable universe, the fraction we can see. Beyond that, space may stretch infinitely, filled with more stars than numbers could ever describe. What does this mean for us? It means that somewhere out there, right now, another star is being born. Another planet is forming oceans, another sunset or sunrises or double sunsets is painting an alien sky. The universe isn't just vast, it's alive with possibility, a canvas so grand it makes Earth's deserts look like a single brushstroke in comparison. The next time you stand on a beach, let the sand slip through your fingers and remember, you're holding a fraction of the universe's smallest wonders, while overhead, the true immensity of creation stretches further than any mind can fathom. In the vast emptiness between stars, there's a silence so absolute it would drive any human mad. Unlike Earth, where sound waves dance through air, water, and even solid ground, space is a perfect vacuum, a place where molecules are so sparse they can't carry vibrations at all. Those epic sci-fi battles with roaring engines and explosions, pure fantasy. In reality, a supernova could rip a star apart right next to you and you'd hear nothing. Not a whisper, this eerie quiet doesn't just defy Hollywood logic, it reshapes how astronauts experience space. Floating outside the International Space Station, there's no rustling of equipment, no hum of machinery, just the deafening absence of noise. That's why spacewalkers rely entirely on radio waves to communicate. Inside their helmets, microphones pick up vibrations from their vocal cords, converting speech into electromagnetic signals that travel instantly to their crewmates' earpieces. Even a conversation between astronauts just a few feet apart has to bridge the gap via technology, because sound, something we take for granted every second on Earth, simply can't exist in the void. But here's the twist, while space itself is silent, the objects within it can simulate sound in unexpected ways. Take the sun, for example. Its churning plasma generates pressure waves that ripple outward, and while these vibrations can't be heard directly, scientists have translated them into eerie, haunting tones by speeding up the data. Similarly, spacecraft like NASA's Voyager probes have captured electromagnetic vibrations in plasma around planets, converted into audible frequencies that reveal crackling, whistling, and even eerie raindrop sounds, proof that while space doesn't transmit sound, it's far from inert. This silence also holds a profound lesson about our place in the cosmos. On Earth, we're enveloped in a constant symphony of life and motion, wind, water, the calls of creatures. But space reminds us that our planet is a rare bubble of noise in a universe that's overwhelmingly, achingly quiet. It's a humbling thought. The same emptiness that muffles sound also cradles the ingredients for life, allowing rare pockets like ours to ring out against the cosmic silence. So next time you hear birds chirping or rain tapping your window, remember those sounds are a cosmic privilege, a fleeting melody in an otherwise soundless sea of stars. Every second, the sun blasts out enough energy to power human civilization for over 500,000 years. But here's the cosmic irony. The light warming your skin today began its journey long before humans walked the Earth. Buried deep in the sun's core, where temperatures reach a staggering 27 million degrees, hydrogen atoms smash together in nuclear fusion, creating helium and releasing energy. But that energy doesn't race straight to the surface. Instead, it embarks on a chaotic 100,000-year odyssey, fighting its way through a dense jungle of plasma in a process so slow it makes continental drift look speedy. Picture a single photon born in the sun's core. It's instantly absorbed by a nearby atom, then re-emitted in a random direction, only to be swallowed up again after traveling less than a millimeter. This cycle repeats trillions of times as the photon bounces through the radiative zone, a region so packed with hot, dense gas that light can't travel freely. It's like trying to walk through a mirrored maze filled with millions of doors, where every step forward sends you backward or sideways. By the time the photon finally reaches the convective zone, about 2/3 of the way to the surface, its journey turns into a slow-motion elevator ride, carried upward by rising bubbles of plasma over thousands of years. The scale of this delay is almost incomprehensible. If that photon left the sun's core when early humans first began using tools, it would only now be escaping into space. What we see as sunlight isn't a live broadcast from the sun's core. It's a delayed echo of ancient nuclear reactions. And here's the wild part. While the energy takes an eternity to escape, the neutrinos produced alongside it zip straight out at nearly the speed of light, arriving at Earth just 8 minutes after creation. That's why neutrino detectors can tell us what's happening in the sun's core right now, while sunlight shows us what happened there back when mammoths still roamed the planet. This sluggish energy crawl isn't just a cosmic curiosity, it's a testament to the sun's incredible density. The core's pressure is 250 billion times stronger than Earth's atmosphere, turning the sun's interior into an obstacle course where even light struggles to break free. Yet without this slow dance of absorption and emission, the sun wouldn't shine steadily. That 100,000-year buffer acts like a cosmic capacitor, smoothing out the fusion furnaces burst into the reliable glow that's nurtured life for billions of years. So the next time sunlight touches your face, remember, you're feeling energy that predates cities, languages, even the very concept of timekeeping. The sun doesn't just light our days, it connects us to an ancient past, one slow-motion photon at a time. At this very moment, as you gaze up at the moon floating peacefully in the night sky, you're looking at a cosmic gap so spacious it could swallow every other planet in our solar system with room to spare. Measure the total width of Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune side by side, all 382,000 kilometers of them, and you'd still have 2,000 kilometers of breathing space before their combined bulk reached lunar orbit. Picture this planetary sandwich. Start with tiny Mercury, barely bigger than Earth's moon, then stack Venus with its thick, toxic clouds. Add rusty Mars, followed by the gas giants Jupiter's great red spot alone could swallow Earth whole, while Saturn's breathtaking rings stretch wide enough to fit 6 Earths across. Toss in ice giants Uranus and Neptune, and you've assembled a celestial conga line spanning nearly the exact average distance between Earth and its lunar companion. Here's what makes this fact so astonishing. We're not talking about some hypothetical alignment. This cosmic parking space exists every single day, as routine as sunrise. The moon's orbit averages 384,000 kilometers away, but the true distance fluctuates between 356 and 406,000 kilometers due to its elliptical path. Even at its closest approach, the 7-planet stack would only poke about 26,000 kilometers beyond lunar orbit, a cosmic near miss by astronomical standards. But this mind-bending comparison reveals something deeper about our place in the cosmos. Despite Jupiter's overwhelming size, large enough to contain every other planet combined twice over, space remains so incomprehensibly vast that even our local Earth-Moon system feels roomy by comparison. Those textbook illustrations showing planets huddled together, pure artistic license. In reality, the solar system is mostly emptiness, with distances so vast they make even Jupiter seem like a speck. Imagine floating at the center of this planetary lineup. To one side, Earth's vibrant blue marble teeming with life. To the other, our cratered moon keeping silent watch. And stretched between them, a parade of worlds representing the solar system's full diversity, from scorched Mercury to frozen Neptune, each a starkly unique realm. Yet for all their grandeur, these planets would appear as nothing more than bright dots in this arrangement. Jupiter, even at just 4% of its actual distance, would still only show as a fingernail-sized disk. Space doesn't just dwarf our planetary neighbors, it humbles our very perception of distance. The next time you see the moon hanging in twilight, remember, you're looking at a cosmic measuring tape, marking a void so spacious it could hold the solar system's greatest wonders with ease. The craziest part about time travel, we've already done it, just not the way sci-fi movies show. Every astronaut who's orbited Earth has technically journeyed into the future, even if only by microseconds. This isn't some theoretical thought experiment, it's direct proof of Einstein's relativity in action. When Scott Kelly spent 340 days aboard the International Space Station, he returned to Earth having aged about 28 microseconds less than his identical twin Mark back on the ground. That tiny difference might seem insignificant, but it reveals the universe's shocking truth. Speed literally slows down time. Here's how it works. According to special relativity, the faster you move through space, the slower you experience time compared to someone standing still. Imagine two synchronized clocks. One stays on Earth while the other rockets into orbit at 17,500 miles per hour. From Earth's perspective, the orbiting clock ticks slightly slower because it's in motion. This effect, called time dilation, means astronauts aren't just exploring space, they're surfing the leading edge of time itself. But what if we crank this effect to the extreme? Picture a futuristic starship accelerating to 99.9% of light speed. For the crew, time would crawl. A 5-year mission might feel like mere months, while back on Earth, decades or even centuries could pass. Come home and you'd find everyone you knew long gone, replaced by descendants living in a world you barely recognize. This isn't fantasy, the math checks out. At those speeds, the time dilation factor becomes enormous. 1 year aboard the ship could equal hundreds on Earth, effectively launching travelers into the future. The real kicker, we've already built machines that exploit this effect daily, just on a microscopic scale. Particle accelerators like the Large Hadron Collider routinely hurl protons to 99.9999% light speed. From the proton's perspective, its brief existence stretches far longer than it should, allowing these tiny particles to live long enough to reach detectors that would otherwise be impossibly distant. Humanity's first proper time machine might not involve flux capacitors or wormholes, but something far more plausible. A generation ship designed to sustain crew for centuries at near light speeds. While we're nowhere near the technology to build one, the physics is ironclad. The universe hands us a free ticket to the future. We just need the courage and the propulsion to punch it. Until then, every astronaut floating above Earth is quietly proving that the most mind-bending parts of Einstein's universe aren't locked in equations. They're happening right now, right overhead, ticking away microseconds at a time, stretching an almost incomprehensible 10 billion light-years across the cosmos. The Hercules Corona Borealis Great Wall isn't just a structure. It's a cosmic titan that defies our understanding of how the universe organizes itself. Discovered in 2013 by mapping gamma ray bursts, the most violent explosions in the universe. This gargantuan filament of galaxies is so vast it would take light, the fastest thing we know, 10 billion years to traverse from one end to the other. That's roughly 3/4 the diameter of the observable universe itself. To put that in perspective, if our Milky Way were the size of a marble, this structure would span the width of the continental United States. What makes this discovery so unsettling is that it seems to break one of cosmology's foundational rules, the cosmological principle, which states that on large scales, the universe should appear roughly uniform no matter where you look. Yet here we have a wall of galaxies over 7 billion light-years long, clustering in a way that shouldn't be possible under current models. Imagine stirring cream into coffee and finding, instead of an even blend, a single thread of cream stretching uninterrupted from rim to rim. That's the level of anomaly we're dealing with. How could something this colossal form? The leading theories involve primordial quantum fluctuations, tiny ripples in the fabric of spacetime from the universe's first moments, that somehow grew wildly out of proportion during cosmic inflation. Another possibility is that we're seeing the ghostly imprint of gravitational waves from an era before the Big Bang, warping the distribution of matter in ways we don't yet understand. But the most unsettling idea that the Great Wall isn't just a fluke. It's a signpost pointing to even larger structures beyond our observational horizon, hinting at a universe far more lumpy and asymmetrical than we ever imagined. Here's the twist: we might never fully map this behemoth. Because of the universe's expansion, light from the far side of the Great Wall hasn't reached us yet, and never will, thanks to dark energy's accelerating push. What we're seeing is essentially a fossil, a frozen snapshot of a structure that's already been stretched and diluted by cosmic time. Future astronomers, billions of years from now, won't even know it existed. The Hercules Corona Borealis Great Wall is more than a record breaker. It's a cosmic riddle scribbled across the sky, forcing us to question whether the universe truly plays by the rules we've written. Every time we think we've grasped the scale of existence, the cosmos humbles us with another reminder. We're just beginning to read the story, and the plot twists are far from over. If you think your work week drags on, try living on Mercury, where a single day lasts longer than half an Earth year. This scorched world spins so slowly that sunrise to sunrise takes a staggering 176 Earth days. But here's the cosmic paradox: because Mercury zips around the Sun every 88 days, a full Mercurian day actually spans 2 of its years. That means you'd celebrate 2 birthdays before your first morning coffee even finished brewing. This bizarre timescale comes from Mercury's peculiar dance with the Sun, a gravitational tango called a 3-to-2 spin orbit resonance. Most planets eventually become tidally locked, like the Moon showing only one face to Earth. But Mercury's elliptical orbit and close proximity to the Sun created a different rhythm. Picture a figure skater pulling their arms in to spin faster, except in Mercury's case, the Sun's gravity yanks so unevenly that the planet rotates exactly 3 times for every 2 trips around its orbit. This keeps it perpetually out of sync, ensuring no single side always faces the Sun. The effects are extreme. During Mercury's endless days, surface temperatures soar to 800 degrees Fahrenheit, hot enough to melt lead, while the pitch-black nights plunge to -290 degrees. Without an atmosphere to redistribute heat, these aren't gentle transitions but violent swings between inferno and deep freeze. Imagine standing on Mercury's surface as the Sun creeps overhead, growing 11 times larger than it appears from Earth. Over weeks, the ground beneath you would literally bake, cracking like dried mud. Then, as the Sun finally sets, darkness lingers for months, turning rocks so cold they'd shatter at a touch. This extreme environment makes Mercury a world of contradictions. Some craters near its poles hide permanent shadows where ice survives just miles from scorching plains. The planet's iron core, making up 85% of its radius, generates a magnetic field, yet solar winds pummel the surface unimpeded. Even time itself behaves differently here. A single Mercurian solar day, the time between one noon and the next, lasts twice as long as its year, a cosmic clockwork that defies earthly intuition. Every visit by probes like NAS, a messenger reveals new surprises, from mysterious hollows in the terrain to unexpected chemical elements in its thin exosphere. Mercury isn't just a dead rock, it's a laboratory for how planets evolve under the sun's relentless grip. So the next time you complain about a long day, remember, somewhere out there, a world is turning so slowly that seasons change before its residents ever see dusk. For decades, the Big Bang has been taught as the ultimate beginning, a fiery moment when space, time, and matter burst into existence. But what if that explosive birth wasn't the true start of everything? Cutting-edge physics now suggests our universe might be just one chapter in an endless cosmic story, with the Big Bang more like a reboot than a genesis. Take the Big Bounce theory, a radical idea that flips the script entirely. Instead of a singularity exploding from nothing, this model proposes that our universe is the reincarnation of a previous one that collapsed under its own gravity. Picture a cosmic accordion, first contraction, then rebound. In this scenario, the Big Bang wasn't a beginning but a reset, triggered when a prior universe reached maximum density and bounced back outward. The laws of physics as we know them might have been rewritten during that transition, erasing any evidence of what came before except, perhaps, for subtle fingerprints hidden in the oldest light we can see. And that light holds tantalizing clues. The cosmic microwave background, the afterglow of the Big Bang, reveals odd anomalies that don't quite fit the standard model. Some regions appear suspiciously colder than others, while large-scale patterns suggest the universe might have preferred directions like faint brushstrokes from an earlier era. Could these be echoes of a pre-Big Bang universe? Some theorists argue these irregularities align with predictions of cyclic models, where each iteration leaves faint imprints on the next. Then there's the multiverse angle. Imagine our Big Bang as just one bubble in an infinite froth of universes, each with its own physics, its own timeline. In this view, the beginning is an illusion, a local event in an eternal, ever-branching cosmos where universes sprout from black holes, collide, or even evolve like living organisms. String theory takes it further, suggesting our three-dimensional reality could be a membrane floating in higher dimensional space, with Big Bangs triggered when membranes collide. The most mind-bending part, these ideas aren't pure speculation. Observations of dark energy, quantum fluctuations, and even black hole behavior hint that our universe's birth might be part of something far grander. The next generation of telescopes, like the James Webb successors, could hunt for more definitive evidence, perhaps detecting gravitational waves from the universe's first second or finding patterns in the microwave background that point to a cyclical past. Whether the truth is a bounce, a bubble, or something beyond our current math, one thing's clear: the Big Bang may have been less of a beginning and more like turning a page in a book we're only starting to read. The universe's origin story might still be waiting to be written or rewritten. Deep in the heart of the Milky Way, floating near the galactic center, there's a cloud so vast and so intoxicating it could fuel a party for every civilization that ever existed. 10 billion liters of pure alcohol swirling in the cosmic void. Known as Sagittarius B2, this interstellar molecular cloud contains enough ethanol to fill every ocean on Earth, and then some. To put that in perspective, if you poured every beer, wine, and spirit ever produced by humanity into one colossal cocktail, it wouldn't even make a dent in this cosmic distillery. But don't start drafting your interstellar bar menu just yet. While Sagittarius B2 is brimming with ethyl alcohol, the same compound that gives liquor its kick, it's not exactly drinkable. The cloud spans light years across, with its boozy molecules spread so thin you'd freeze or suffocate long before catching a buzz. And even if you could gather a glassful, it's laced with toxic methanol and other chemicals that would make it about as pleasant as rocket fuel. Still, the sheer scale of this celestial speakeasy is staggering. Somewhere out there, nature has been quietly brewing on a galactic scale for billions of years. What's even wilder is how this cosmic cocktail formed in the first place. The alcohol isn't floating freely, it's clinging to microscopic dust grains, where chemical reactions between starlight and simple molecules like carbon monoxide slowly build complex organic compounds. Over eons, these icy grains clumped together, creating vast reservoirs of molecules that, under the right conditions, could someday become the building blocks of life. Sagittarius B2 isn't just a curiosity, it's proof that the universe has a knack for organic chemistry, mixing up the ingredients for complexity long before planets or bartenders existed. Now here's a twist that'll make you rethink the phrase "age to perfection." Some of the alcohol in this cloud isn't just ethanol, it's vinyl alcohol, a molecule that's crucial for forming fatty acids, the very compounds that make up cell membranes. That means this interstellar happy hour might hold clues to how life's essential structures first emerged in the cosmos. It's as if the galaxy set up a chemical laboratory billions of years ago, experimenting with the precursors to biology itself. So while we won't be opening a space-age brewery anytime soon, Sagittarius B2 reminds us that the universe is far more inventive than we are. Between the raspberry-scented nebulae and rum-drenched clouds, it's clear the cosmos doesn't just create stars and planets. It cooks up an entire molecular feast with flavors stranger than anything we've ever tasted. Who knows, maybe one day when we're sipping drinks made from comet ice or asteroid minerals, we'll toast to the original cosmic mixologist, the galaxy itself. The universe we can see, the glittering expanse of galaxies stretching back 13.8 billion years, might be nothing more than a speck of dust in an unimaginably vast attic. Here's the staggering truth: everything we've ever observed, from the closest star to the most distant quasar, could be less than a drop in the cosmic ocean. The reason lies in a concept called inflationary cosmology, and it suggests that the Big Bang wasn't just the beginning of our universe. It might have been the birth of an infinite multiverse, with realities beyond our horizon forever out of reach. Picture this: in the first trillionth of a second after the Big Bang, space itself didn't just expand, it exploded, inflating faster than light could keep up. This hyper-stretch, driven by a mysterious force called the inflaton field, smoothed the universe to near-perfect uniformity and set the stage for everything to come. But here's the twist: once inflation starts, theoretical physics suggests it might never truly stop. Instead, it could keep spawning bubble universes endlessly, like soap suds forming in an unending bath. Our entire observable cosmos, with its hundreds of billions of galaxies, might just be one accidental bubble in an infinite froth of other universes, each with different physical laws, different constants, maybe even different dimensions. The evidence for this radical idea is etched into the oldest light we can see: the cosmic microwave background. Those tiny temperature fluctuations, the ones that seeded all the galaxies and voids we know. They match predictions of inflation to an eerie degree, but they also hint at something even weirder. Some regions of the microwave background appear slightly colder or hotter than expected, as if our universe collided with another bubble long ago. It's like finding a fingerprint on a window pane, proof that something might exist just beyond the glass, and that's where the real mind bender kicks in. Due to the universe's accelerating expansion, light from anything beyond about 18 billion light-years away will never reach us. Space itself is stretching too fast for those photons to catch up. That means entire universes could be hovering just out of view, forever hidden by the sheer speed of cosmic inflation. Some theories even propose that other bubbles might have entirely different physics, places where gravity repels instead of attracts, or where time runs backward. The most unsettling part: we might never know for sure. If other universes exist beyond our cosmic horizon, they're not just distant. They're fundamentally disconnected, separated by stretches of inflating space that no signal, no probe, no math could ever bridge. Our observable universe, for all its splendor, might be a lonely island in a sea of infinity, surrounded by shores we'll never walk. Yet this isn't just philosophical speculation. If the multiverse is real, it could solve one of physics' biggest puzzles: why our universe seems so fine-tuned for life. With infinite variations statistically, some bubbles had to hit the jackpot. We might not be special, just lucky. The next generation of telescopes could hunt for more clues, like gravitational waves from the Big Bang or anomalies in the microwave background that betray collisions with other bubbles. Until then, the greatest lesson might be humility. We've spent centuries mapping the cosmos, only to realize we might be staring at a single grain of sand on an endless beach, where every grain is a universe unto itself. From black holes bending time like taffy to diamond planets bigger than Earth, we've journeyed through a universe that constantly defies our wildest imaginations. Think about it. Light takes millennia to cross our galaxy, while quantum particles instantly mirror each other across cosmic distances. Stars older than the universe itself whisper secrets we're only beginning to decode, and entire galaxies are being yanked toward invisible giants we can't even see. These aren't just tidbits for trivia night, they're glimpses into a reality far stranger, far more dynamic than anything our ancestors dared to dream. What ties these discoveries together? They all shatter the illusion that space and time are mere backdrops to existence. Time isn't a steady river, it's a twisting, swirling current, changing speed near black holes or even on different floors of a skyscraper. Space isn't empty, it's a seething quantum foam where particles flicker in and out of existence, and galaxies are just specks in an ocean of inflating universes we'll never reach. Even the Moon, our closest companion, is inching away so relentlessly that future civilizations will see a far smaller crescent in their skies. But here's the real magic: every one of these facts started as someone's outrageous hypothesis before evidence proved it true. That's why cosmic mysteries matter. They remind us that reality is always richer than our assumptions. Maybe you're most stunned by the Great Attractor pulling thousands of galaxies, or the holographic theory suggesting our 3D world might be a shadow on a distant 2D surface. Whatever resonates, remember, this isn't just science. It's an invitation to stay curious, to question, and to marvel. So tell us which fact rewired your brain. Drop it in the comments, and if you're hungry for more mind-bending journeys, hit that subscribe button. The universe has endless surprises waiting, and we're just getting started. Until next time, keep looking up and never stop wondering what else is out there.